In this video, we are going to demonstrate a very popular experiment, and that is falling of a magnet through a copper pipe. First, we are going to ask some of our colleagues what they think, how long time it takes for this neodymium magnet to fall through this copper pipe, 1 meter long copper pipe. And after we have asked our colleagues, I'm going to explain a bit about the science and the math related to this problem. So we have the copper tube. Okay, let's have a look again. All right, we have a neodymium magnet, and we also have a kind of a plug, let's say, that has pretty much exactly the same weight and diameter as this magnet. And we are going to use this to compare the magnetic drag versus the aerodynamic drag. We are going to do the maths and this comparison at the end. Are you filming?
Yes.
Yes, okay. So this is a 1 meter long copper pipe, almost 100% pure copper. And this is a neodymium magnet. And I'm going to drop it into the pipe.
Yeah.
And you have to guess how long do you think it will take for the magnet to come out at the other end of this pipe.
Okay, 1.57 seconds.
1.57 seconds, very precise. What do you think, Päivi?
No idea.
Well, make a guess. That's the name of the game. Whoever gets the closest gets a palkinto, okay? I have a palkinto ready.
I don't even know what the palkinto is.
It's a little Toblerone that. But yeah. I will have to edit this one out. Just say number when you're ready, because
It won't come out.
it will not come out. Okay, that's
Okay.
an interesting one. All right, so
Then you go.
all right, when I start dropping it, you just press the start there. Okay, 3. You started already?
No.
Okay.
You
Yes, you
said
did.
when it's no.
Yes, you did start.
Sorry.
Okay, wait. Reset. Okay, okay. Just YKK nyt. No? How much?
7.72, but I think I was a bit slow.
No,
so-
you were very precise actually.
So, are you now going to kick my ass?
No. All right. So this is a copper pipe.
Yes.
It's basically 100% pure copper. Basically, it's
I see.
99.9%
Yeah.
pure copper, and this is a strong neodymium or some other earth metal magnet.
Yes.
Show him that it doesn't attach to the copper.
Right.
Okay, and now you're gonna.
I'm
Do
going to drop this magnet through this copper pipe.
Okay, and
So how much time do you think it will take for this magnet to come out from the pipe?
I
The
haven't
pipe
seen
is
inside
what,
the
1
pipe.
meter long?
Show him inside the pipe.
No glue.
Okay,
Right.
How long?
How long?
because you're asking that way, I'm gonna say something ridiculous like
Okay.
10 seconds.
Okay. Go.
Do you have a timer?
Well, it's
Yes, I actually have.
Right. Tell me when.
you have to edit this.
this.
Yeah.
Okay, tell me when.
Yes, it's working. Okay,
Now?
when I do this.
Okay.
It's gonna hit 10 Oh, 7.
7 seconds.
About 7 seconds.
Okay. All right, Ashkan. So, copper pipe, practically 100% pure copper,
Okay.
and the neodymium magnet.
Okay. So it's not. It's not. Okay.
It's
Okay.
not. It's not attached.
Okay.
Okay. Now I'm going to drop this magnet into the pipe, and
Okay.
the question is, what do you think? How long will it take for this magnet to come out from this pipe?
I think it will be. Well, this is how long it is?
It's 1 meter.
1 meter.
Yes.
Oh, I'd be.
Meaning I'm really short.
Yeah, 1.5 seconds.
1.5 seconds.
Yeah.
Okay. So start the timer and tell me when I drop it. So tell me when, and I will drop it at that moment.
Okay, 1, 2, 3. Okay,
So
see 8 seconds.
8 seconds. Okay.
I
So
was wrong.
You were a bit wrong. Okay.
Yeah, not big a lot.
And at this point, you are not the closest guy. We will let you know who's the winner at the end.
Okay.
Thank you, Ashkan.
No problem.
Okay.
Thanks so much.
All right, welcome back. So we are going to talk a little bit about the science and the delicious mathematics that go into this problem. But first, let's see. There is this stainless steel plug which we made from some bolt, a few washers and a few nuts. It has the same diameter as the magnet and practically the same weight. And let's see how quickly this goes through our pipe. Yeah. We measure this to be 0.65 seconds. So it's very, very quick. So what happens when the magnet is falling through this copper pipe? So the magnet has, of course, a magnetic field around it. And as the magnet is moving, from the point of view of the copper pipe, there is a changing magnetic field. According to the Lenz's law, the magnetic field in the pipe will induce an electric current which will try to actually stop the magnet from movement. It's going to oppose the change of the magnetic field which has generated that current. Now, basically this changing of the magnetic field or magnetic flux we can describe through the velocity. So we have here a differential equation that tries to describe this system. On the left hand side we have the total force that is operating on the falling magnet. We have a mass and we have the acceleration. On the right hand side we have the other forces broken down. First of all, the gravitational force, so mass times gravitational constant. Then we have this electrodynamic drag force, which I have noted as C1 times V. So this V is denoting the changing of the magnetic flux, and C1 is a constant which depends on the thickness of the copper tube, the strength of the magnet, the conductivity of the material of the tube, so conductivity of copper, and also the diameter of the pipe. So all these factors determine how much is this constant. Then here we have two forces. One is coming from the Stokes law, and both pertain to aerodynamic drag. The first one, the Stokes law, works in a case of laminar flow and low velocities. The other one, which is called drag formula, it works at higher velocities and turbulent flow. This part we can very safely ignore, because with these diameters and at these speeds, this is completely negligible. Basically, this part that is coming from Stokes' law is also negligible, but we can easily solve this equation even if we take it into consideration. So, this is the solution of the differential equation. So v as a function of time is equals to the terminal velocity times this factor. And we see that we have 1 minus e on the power of t divided by tau. Tau is the time constant of this system, and it's equal to the mass of the magnet divided by these two constants that we have here. Terminal velocity is basically this time constant multiplied by the gravitational constant. If we neglect the aerodynamic drag, then our time constant will be this, and the terminal velocity will be this. It's important, again, to note that both this time constant and the terminal velocity depend, as I said, on the conductivity of the pipe, on the diameter of the pipe, the thickness of the wall, and the strength of the magnet. Yeah, so Yipe, because you guessed the time that it takes for that magnet to go through the copper pipe, your guess was the closest to the actual time.
Okay, and it was.
The actual time is actually 6.6 seconds.
Okay.
Right? So, and you guessed 10 seconds.
Yeah.
And so you were the closest of everybody who we asked. So you get this reward. Supla patukka.
Oh, thank you.
Ooh.
Thank you for this nice supla patukka.